And Clément, it's up to you.
Okay, so hello everybody. Today we are going to speak about machine learning. The plan for today's presentation is quite simple. First of all, we are going to present the tool we're going to use during the presentation. Then I'm going to make a very short introduction about machine learning and supervised learning and what it is. And then we're going to realize a very simple task. We're going to solve a problem with a logistic regression, and we're going to use this logistic regression in order to introduce lots of the key components of the deep learning. And finally, we're going to realize a really simple image classification task using deep learning. So we're going to work on the MNIST dataset, which is a dataset with 10 digits, 0, 1, 2, 3, etc. And the main goal is to classify the digit. Given the image, we want to guess if it's a 0, a 1, etc. So first, the tools presentation. So today we're going to use Google Colab. So Google Colab is a notebook, but you can run it on a navigator. So I don't know if you can see, but I think in the conversation part of the Zoom, I've put two links. And by clicking on this two link, you have access to the code we're going to use today. And the framework that we're going to use is PyTorch. So PyTorch is a framework in order to realize deep learning. And so to be honest, most of the time when I'm using PyTorch, I'm using it using Python. But now it is possible to use PyTorch on R. So today we're going to use R to use PyTorch. But as I discussed earlier with Mathieu, when you've got some problem with PyTorch, it's easier to find your answer on the forum when you use Python, because most of the people are using Python. But it's absolutely okay to use R if you prefer. And today it will be in R, of course. So first, I'm going to do a really small introduction about machine learning and supervised learning. So here is a definition of the machine learning. It is the study of computer algorithms that improve automatically through experience. It is seen as a part of artificial intelligence. Machine learning algorithms build a model based on sample data, known as training data, in order to make predictions or decisions without being explicitly programmed to do so. So here there are three important notions: the notion of computer algorithm, of course, the notion of training data. So when you want to realize machine learning algorithm, you will need to collect data, and your algorithm will train on this training data. And the fact that the algorithm is not explicitly programmed to do something. So what it means is that the programmer is not going to explicitly describe the rule, and the algorithm will only learn from the data. So if we take a really simple example, if you want to realize an algorithm that distinguishes apple from banana, you've got two ways to solve this problem. You can realize a rule-based algorithm. So the programmer will define his own rule. So for example, you will try to have the color of the majority of the pixel. If there are a majority of pixels that are red, maybe you'll say, okay, it's an apple. If it's yellow, you'll say, oh, it's probably a banana. You can look at the shape of the image, and so you can design your own rule as a programmer. But here, it's not what we want to do. We are going to use a machine learning approach. So in a machine learning approach, you just send example of apples and bananas, and you say, so, okay, this is an apple, this is an apple, this is an apple. And the algorithm will run the underlying concept of apple and bananas. So we will try, we will understand during this presentation, I hope, how it works. In this presentation, we're going to focus on the supervised learning part of the machine learning. So there are other parts, unsupervised, semi-supervised, reinforcement learning, but today we're going to focus on the supervised learning part. And so the supervised learning is a machine learning task of learning a function that maps an input to an output based on example input-output pairs. So Sometimes you think that there is a causal relationship between some input data and some output data. And so it means that it exists a mathematical function that goes from the input data to the output data. And when you use supervised learning, the aim is to try to approximate this mathematical function using some algorithm. So today we are only going to focus on supervised learning tasks, which means that you're going to need to collect data. So when you collect data, so for example, one example of supervised learning, you can have genetic data and you want to try to predict the disease risk. And so when you collect the data, the first things that you want to do is to split the data into a training set and a test set. So the training set is the data that you're going to use in order to train your algorithm. And the test set, you will use it in order to have an idea of the performance of the algorithm. So it is really important not to add the indicator of performance using the training set, because when you train an algorithm, you've got a few possibilities. You can realize underfitting. What it means when you realize underfitting is that you absolutely not understand the mathematical functions. So here, for example, we've got some data points, and we can see that the function is not, it's clearly not good to approximate the data points. Then you can have a good fit. So a good fit is some good approximation, but it's not the perfect approximation, because the final possibility is the overfitting. And in overfitting, actually, the problem is that the analogy that we can use about overfitting is that, for example, a student that will learn by heart for an exam. So if he learns by heart, he will go to the exam, and if he's got exactly the same question, he's going to be able to answer the question. But if the question is slightly different, he will struggle to find a good answer. So when you realize overfitting, it means you will have maybe very good performance on the training set, but actually you will have bad performance on the test set. So that's why it's really important to split your data into a training set in which you're going to train your algorithm, and a test set on which you're going to see the performance of your algorithm. So now that we have this in mind, we're going to use a very simple example, and we're going to speak about the logistic regression. And I'm going to use the logistic regression in order to speak about the key components of the deep learning. So during this presentation, we're going to look at several key components. The first component is a neuron, the layers, the weights, the gradient descent, the loss function, the activation function, and the epochs. And so slide after slide, we're going to see all this notion. So for that, I've created a very small problem. So a strange disease has appeared and is affecting more and more people. However, a brilliant team of researchers noticed that not all individuals were susceptible to this disease. They identified two criteria that seem to be determining factors: age and physical fitness. They want to build an algorithm that takes these two variables as input and indicates at the output whether or not one is likely to get sick. So the idea is that we're going to have two input variables, age and physical fitness. So in fact, I've generated a completely random variable we are going to see, but it's easier to have a story behind that. And what we want is to predict the disease risk. So we're going to use a machine learning approach. So the researcher obtained data for some individuals, and they decide to plot them on a graph. And what we can see on this graph is that these data are linearly separable. So what it means is that we're able to separate the data with a line. And so when it's the case, you want to use a logistic regression. So on the first notebook, I've generated this data. And so here is a representation of the data. And the first thing that I've done is to split my data set into training sets and test sets. So I've used the function sample from R, and now I've got data train, which will contain the training data, and data test, which is the test data. Okay, so back to the presentation. What we want to do is to create to obtain some probability for each individuals. So we can introduce the first two notions of deep learning. So the notion of neurons. Neurons is an object that hold a number, and the notion of weights that are parameters that linearly transform the data. So for our specific example here, X would be the age, Y the physical fitness. And so it is in a neuron, and we will obtain a new neurons, which is the linear combination of the input variables. And finally, so this is the new neuron, and this neuron has any real value can be contained in this neuron, and we want to obtain a probability. So we will use sorry, I just see the question. Oh, okay, perfect. So sorry. And then we are going to go through a sigmoid function. And so the sigmoid function allows us to go from any real values to a value between 0 and 1. So as we can see here, any real value will be contained in 0 and 1. And it will allow us to obtain a probability. So now we have our logistic regression algorithm. We've got our input data. It will be transformed linearly, and finally it will go through a sigmoid function in order to obtain such a thing as a probability. And so all the point of the logistic regression algorithm is to find the good value for W1, W2, and B. And we're going to see how to do that. And for that, I need to introduce a new notion of the deep learning, which is the loss function. So the loss function is a function to evaluate the quality of the modeling of your dataset by your algorithm. So the aim is to find the best W1, W2, and B in order to minimize our loss function. So for our specific problem here, which is a binary classification, we're going to use the loss function, the binary cross entropy. So here is the formula of the binary cross entropy. And so we realized it on all the data. So from 1 to n corresponds to the number of data points. And so I'm not going to dig into the details of the formula, but what we need to understand is that this loss, when the true label of the data is 1, you want to predict a probability that is as close as possible to 1. And if you have a probability that is close to 0 and the true label is 1, you will have a very big loss. So the idea is to find the best value of the weights that allows us to have a probability that tends to be the true probability of being the label. And so now we've got all our elements to train our logistic regression. So the first step is to just put some random value for our weights. So you can put any value. Then once you've put this value, we're going to compute the probability on our training data. So all our training data will go through the very small neural networks that we have defined here. And we're going to obtain probability for each data point. So of course, at the beginning, as the weights were completely random, the probability will absolutely not represent the good probability. But then we're going to compute the gradient of the loss function. So remember, the loss function allows us to know how our algorithms are performing. And once we've computed the gradient of the loss, we're going to use an algorithm which is called the gradient descent that will allow us to update the value of our weights. So step after step, we're going to slightly change the value of our weights in order to find the good value of W1, the good value of W2, and the good value of B in order to minimize the loss function. And so if we really minimize the loss function, the probability that we obtain thanks to our logistic regression will allow us to predict the probability of the patient to be sick or not sick. And so we do that on all the data points that we have on our training data. And sometimes, if the problem is quite difficult, it could be interesting to go several times through the same training data. So each time you go through all the training data is called an epoch. So this is one of the other components of deep learning, the epoch. So if we take our code now to see how it looks, so I've decided not to run the cell during the presentation because some cells are quite time consuming. So here, this cell allows us to install PyTorch. So if you want to run it, you will have to run this cell. Here we load the relevant libraries, so Torch Vision and Torch, which is related to PyTorch. This block of code is not really interesting. It's actually some pre-processing of the data in order to be able to use the data in the PyTorch framework. So we just transform the data that we obtain here into a new format that will allow us to use PyTorch. And here we convert our data frame object into a data loader object. And so it's not really interesting. On any tutorial, you will find that. And so it allows us to train the data because we need the format data loader. And here is the first interesting thing in this cell. We will define our neural network. So I want to insist on that. It's a logistic regression, but we can do a logistic regression with deep learning framework because it's actually the same. And so what we say is that we want one layer of neurons. So we've got two because we have two input variables and we want one output variables. And so I've called it FC1 for fully connected. And so here we say when the data goes through the neural network, it will first go through the fully connected layer and then it will go through a sigmoid function. So here we define the network. This is exactly the same as and so here we say, okay, this is the model. Optimizer. Optimizer is related to the algorithm that we want to use for the gradient descent. So remember, the gradient descent allows us to update the parameter of the function of the network according to the loss function. So here we want to use the optim Adam. So I'm not going to dig into the details of what is Adam. And here, so for the moment, we've just defined the network, but for the moment, the value of the weights are completely random. So now the goal is to update the value of these weights using the training part. So using our training data. And that's what we're going to do here. So for epoch in number of epoch. So each time I go through this loop, I'm going to see all the training data. And so the first part is to initialize the gradient to 0 for the moment. Then we take all our training data, our input data, and we put them in the network and we obtain the outputs. So it goes through the different layers of neurons and we obtain our outputs. And then we compute our loss function. So we compare the output with the true label. So here, this represents the true label, and this represents the output that we obtain. So it allows us to compute the loss function. And then we realize a step of optimization in order to slightly change the value of the parameters. And so we obtain our loss for each loop. So here, as the problem is really simple, I've realized only one epoch. And then what we want to do once we have trained our algorithm is to test the performance of the algorithm. And remember, if we want to test the performance, we're going to use a test dataset. So that's why here is test. And so we put all the data from the test dataset through the model. So now the model is trained. So we hope that the probability that we obtain will correspond to the true value. And so after that, I've predict for each test data point, I've predict what the label is, and I compared it to the true label. And so for this really simple problem, we can see that I've got an accuracy of 99%. So it's actually not a performance because the problem is very simple. So don't hesitate if you have questions, but please ask the question with the mic because I'm not sure I can see it when it's on the conversation.
I'll let you know if there's
for the
questions,
moment,
don't worry.
we've used. Okay, perfect, thank you. So for the moment, we've used our deep learning framework, PyTorch, in order to do a logistic regression. And actually, you will see that logistic regression is very close to a neural network, a deep neural network. So I've put here some remember of what we want to cover. So we can see that we already know now what is a neuron, what is a weight, what is a gradient descent, the loss function, and the epochs. And we want now to define what is a layer and what is the activation function. So thanks to the brilliant work of the researcher, it was possible to isolate patients at risk of contracting the disease, and the first battle was successfully won. Unfortunately, the virus has mutated, and it seems that the condition on the criteria is not exactly the same anymore. So the researchers then decide to conduct a new investigation campaign. So now the data looks like that. And what we can see is that now it's not linearly separable. So the logistic regression will not work at all. And that's why we're going to use the deep learning. So we're going to take the small neural networks that we have defined, and we're going to add some modification in order to convert it into neural networks that will enable us to solve the problem. So the first modification that we're going to make is to add a layer of neurons. So remember, in the first part, these input neurons were directly connected to the output neuron. And now there is an intermediate layer of neurons, and all these neurons are fully connected. And so what you want to say to me is that, yes, but for the moment, it is still a linear combination of input variables, because here it will be actually a linear combination of these input variables, and here it will be a linear combination of the linear combination. So at the end of the day, I still have A times X plus B times Y plus C, so it's absolutely not interesting. And so that's why we're going to add a second component in order to obtain a true neural network, which is the activation function. And so what is the activation function? It is a function that we apply to the neuron output signal. So for example, here, I've got a value A, which is the value of these neurons. And instead of feeding these neurons with directly the value A, we're going to, the value A will go through an activation function. So we will obtain this new value, and this new value will go to the neurons through a linear transformation. And so the features of the activation function is the non-linearity. So it exists a theorem called the universal approximation theorem, and it tells us that any continuous function can be approximated by a neural network with a single hidden layer and a finite number of neurons. So thanks to this activation function, it will allow us to go from be able to approximate any linear function to any non-linear function. So really, the activation function is a key component of neural networks. And so it's better if it's everywhere differentiable in order to be able to optimize the loss function with the gradient descent. There are other, this is not exhaustive. I think there are other property of the activation function. So now we've got all our components to realize our neural networks. So if I go back to the code, here I've generated this new data. So we can see that now it's not linearly separable. Once again, I've split my data into a training set and a test set. Here it's the pre-processing of the data, so I'm not going to spend some time here. And now we are going to look at the model. So if we look back to what it should represent, so we've got this first layer that goes from 2 neurons to 3 neurons. So it's actually this part. And a second layer that goes from 3 neurons to one neuron. So it's actually this part. And so when we go forward in the network, we want first to go through the fully connected one layer, so this one. Then this is the activation function. So there are several different activation functions. I've decided to use tanh in this case. And then we go through the second fully connected layer. And finally, we go through the sigmoid function. So I hope that it is clear for everyone that this is exactly the same as this. And so now we define our optimizer. And once again, we're going to train our algorithm. And so here we can see the evolution of the loss function. So this is the value of the loss function on the training data during the training. So we can see that step after step, the loss function is decreasing. The value of the loss function is decreasing. And so then we want to see the performance of our model. And so we're going to do it on the test data sets. And so here the accuracy is 90%. So I think that if I've trained it for a longer time, it will have better performance, but the idea is the same. And what I want to emphasize here is what is the role of the intermediate layer. So what we can notice here is that actually the final part of the neural network is logistic regression. So it means that the data in input of this logistic regression must be linearly separable. Otherwise, it will not be possible for the algorithm to find a way to separate the positive from the negative. So the role of the intermediate layer is to create a new representation of the data in which these two values will be linearly separable. So what I've done for this presentation is that instead of obtaining the final probability of the network, I want the intermediate representation of the data. So I take my test set, I put the value of my test set in the network, and instead of obtaining the probability, I just want the intermediate value that are the value of the intermediate layer. And what I want is to visualize this intermediate layer values and to see if it's clearly linearly separable between the sick people and the safe people. So that's why we have realized here. So here I say, okay, I want the intermediate value of the layer. And using Google Colab, I just had a problem to plot it. So I'm sorry, I'm going to visualize it on Python. So this is approximately the same problem, but on Python. And so here is the value of the intermediate layer. And we can see that these values are actually linearly separable. So the intermediate layer was an intermediate step in order to solve our problem. So I hope that this is clear for everybody, and we're going to go through the final thing, which is a very simple image classification.
Excuse me, I will have a question if you do not mind.
Yeah.
Well, in each epoch, let's say, you make use of some optimizer, which I guess is itself iterative. So you could control the number of iterations of the optimizer, I guess. So my question is, would it be equivalent to use just one epoch with more iterations of the optimizer and several epochs with less iterations of the optimizer, if you know what I mean?
I think I think it's the same thing, but the way it is on the code, I don't know really how to decide the number of steps that you want to realize with the optimizer. So here you define the optimizer. Oh yeah, maybe here you can do you can say to it to realize several steps. But I think it's better to realize epochs because at each training, I think it randomly samples some data. So maybe it's better to realize optimizing step on different samples of data each time.
Okay, okay. I thought it would take the whole data.
Actually there is one notion that I didn't speak about, which is the batch size. So here, for example, I've defined a batch size of 16 data. And so instead of doing it on all the data at each time, we give it 16 data points by 16 data points each time.
Okay, I see, thanks.
So yeah, this is the batch size parameter. So back to the image classification. So first I want to emphasize, so now we have understood a bit the role of the intermediate layer. And so I want to emphasize it with the conceptual idea of deep learning. So when, for example, us are realizing face recognition, what we're going to do, first of all, is that we're going to identify some very low-level features. So for example, we're going to identify some line, or I don't know, some circle. And then we're going to convert these low-level features into higher-level features. So for example, if we see lots of curved line, maybe we'll say, oh, it's probably hair. If we see two circles into two other circles, we'll say it's probably high. And then once we've got these higher-level features, we can have the final conceptual idea of the face. So we go from low-level features to high-level features. And so this is actually what a neural network is doing. So in the first layer of the neural networks, it will learn some low-level features. So I don't know, maybe these neurons will activate only when it recognizes some horizontal line at the top of the image. Or some circle at the bottom of the image, etc. And so it goes from these low-level features through these higher-level features. And so at the end, it's going to make a prediction on the probability of the image being a 7 or the image being a 2. And so to finish this presentation, we are going to do this image classification. So the aim of this algorithm is to have an image in input and to try to predict whether this image is a 0, a 1, a 2, etc., etc. So the code is here. So this is to install PyTorch. As it's a new Google Colab notebook, this is the same code. And so what is cool with PyTorch is that it allows us to obtain dataset directly from PyTorch. So here, when I'm doing MNIST dataset, I get the data directly from PyTorch. So we obtain the data. Here I visualize one of the digits. So this is a 4, for example. Here I convert the format of the data into a data loader, which is a relevant format for PyTorch. And here I define my neural network. So I didn't create this network. I took it from the internet. And so here there is a new notion, which is the convolution layer. So most of the time, this is fully connected layer, which means that all neurons are connected through the next layer of neurons. And so the convolution layer are another type of way to connect the previous layer of neurons to the next layer of neurons. So I'm not sure I've got time to speak about that. If you're interested in it, don't hesitate to ask questions about the convolutional layer at the end of the presentation. So here I've defined a 2-layer of convolutional layer and 2 fully connected layers. And the dropout is a parameter that allows us to deal with overfitting. So when you add dropouts, it's better for overfitting. And here we say, all right, our input data go from the convolutional layer. Then this is an activation function. This is the second layer, a new activation function. Here is a max pool is an operation with the image to reduce the dimension of the image. Dropout is for the overfitting, etc., etc. And at the end, we obtain so these 10 neurons. So if we go back to here, so 10 neurons, and in each neuron, we want such thing as a probability. So for example, I don't know if here we've got 0.1, it means that the neural networks thinks that there is a 10% chance that the image is a 0. And so then we want to train our network. So here we define the network, and now we want to train the network. And so it is almost the same as the previous problem, but here instead of using a binary cross entropy, as there is 10 different classes, we're going to use the cross entropy loss. And so we train our network. So this has trained for a long time actually when I've realized it earlier. And so now we are going to test the performance of our algorithm on the test set. And we can see here the accuracy, and this is 98%, almost 99% with this neural network. So this is quite good. Okay, so at the end of the presentation, don't hesitate if you have questions. I don't know, and if you want to know more about the convolutional operation or other things that was not clear during the presentation.
So yeah, Clément, thanks. It was very interesting, and you have very nice visuals. So before I open the questions, I had a question, an R-rated question. So I know you do machine learning in Python mainly, but you say it's similar in R. Do you know the tidy models framework to do machine learning or not? Have you ever used it or not?
Do you know the what? Sorry.
Tidy models. Have you heard of this or not?
No, sorry.
No. Okay. No. Maybe somebody else has experience. I have never used it, but I know it's a it's a collection of packages like similar to tidyverse to do machine learning in a tidyverse compatible way, and it seemed like pretty neat. So I don't know if someone has any experience with that, but I don't know. It seemed interesting anyway. It seemed like an interesting way to program machine learning. So maybe some other people have questions or comments. Apparently you cannot do deep learning with tidy models yet. So, okay. So I guess this would be a... you guys feel free to take the mic if you have a question or a comment.
Yes, so I'm the one who use tidy models a lot.
Cool. So do you have any feedback on that?
Yes, it's a very, very good meta package for machine learning. So you have several packages in it, and unlike Keras, it's decoupling of packages. You have one package for preprocessing called recipes, one package for the specification of model called parsnip, one package for the parameter tuning called tune, etc., etc. And they propose several models, and with a lot of preprocessing steps, and it's really user friendly, and yeah, I highly recommend you to try and use it. Okay, thanks.
I think it's starting to get mature, because I tried it 2 years ago and it was still a little...
Yes, now it's mature, and you have also extra package that are new. For example, you have the usual tuning package, and 1 or 2 months ago, they released a new fine-tune package for other tuning techniques, like racing or simulating annealing, but it's more specific. So you continue to have new packages, but the core tidy model is stable.
Can I have a word?
Yes, sure.
Okay. Just a little bit of the history of this package. I came from the Keras. I'm used to use the Keras package, and then I saw the TD models, and also I saw the model R that is package that came from tidyverse, and it seems that tidy models will supersede the model R. And tidyverse don't have anything connected with tidy models, but it seems they support to that tidy model exists. Okay, they are not the same group, but I recently asked about that if they will support something about that. I say this because I read an article. It's about just the comparison about model R and tidy models. Why should I use one or another? And the author opinion was that model R, it's old, but the things that tidy models at that time was not so good is that it allows the user to make mistakes. It is very it's very how can I say flexible, but the way they make the user think may introduce some errors, or may allow the user, if not aware, to have some errors. But I think this is just a point that we should know, just to not make those mistakes. But I think that tidy models is very mature now. And for the record, the Carrot author is the one that started the tidy models package. So he is trying to remake Carrot in a better and modern way, and also having an other package that already exists in R inside the tidy model models world, if I can say. Just a little bit of history about it.
No, interesting. Yeah, you can post the link if you want in the chat to your article.
Yes, and if I can complete, in my opinion, I think modular is dead, and it was developed when a tidy model was very immature, and now it's completely superseded by tidy models. And yes, as you say, tidy models was built upon the tidyverse. And it used tidyverse syntax with pipe and other, it used other dplyr, verb, etc. And it has been written by Max Kuhn to do a restart of Caret with the tidy principles.
Okay, thanks. Interesting. So Clément, there's a few other questions. From Ulrich, is it possible to use NVIDIA's GPU under R's PyTorch? Clément, are you still here?
Sorry, I didn't activate my mic. Yeah, I'm not an expert on this type of question, but I know it's possible if you've got a CUDA compatible GPU. It is possible to use NVIDIA's GPUs under R PyTorch, just as it's possible to use it on Python. It's absolutely the same. And the other question is about tidy models. So I'm going to let and yeah, I've put the right link for the second Google Colab notebook.
Ah, thanks. Yeah, I had the same issue. Anybody has other questions? I had another one. Do you have a document you recommend for beginners doing machine learning, like a reference?
It depends if it's machine learning or deep learning. So if you want to do deep learning, I think the documentation of PyTorch and Keras, which is TensorFlow, actually are quite good. And you've got several very simple examples. So for example, the MNIST dataset is a very classic example, and it is both in Keras and PyTorch. So yeah, the documentation is very good.
Okay.
And there are so much content on internet that
No, I know, but sometimes people who know, they have like one or two that they like to.
Yeah, I'm following. So I remember that when I started machine learning, I was on a YouTube channel called Sendex, SENTDEX, and this was very interesting. And Deep Lizard, I saw this link, is also very good.
Okay.
It depends whether you prefer to have some books or some video content. And a book, I can try to remember one. If there is another question, don't hesitate. I will find the right title.
Yeah, don't worry. Yes, so of course the question, R or Python.
And yeah, the book that I recommend is Deep Learning from Jan Goodfellow, the MIT, and it is very good because there is a first part about more the idea behind deep learning and the math behind deep learning, and more generally about machine learning. And then there is some more details about deep learning algorithm.
Awesome, thanks.
And or Python. I think I will say Python, but it's really because most of this framework, like PyTorch or TensorFlow, has been first developed on Python, and most of the people are using Python. So when you've got a problem, it's easier to find your answer in Python than in R, because for example, PyTorch and TensorFlow has been translated in R after Python, but both are very good.
No, and I think now both, I mean, R can do the majority of the basic machine learning, and it's this the inverse in doing stats in Python. Like now you can do a lot, but it comes from, I mean, it's all a mix now.
Yeah. So I think it really depends on you, and there is not a good answer to that. But when you really use deep learning framework, I think it's better to use Python.
No, and the Stack Overflow argument, it's
yeah,
very important.
really the biggest argument, I think.
Okay. And you know, it's tidy models again. Okay, yeah, this I need to try. Okay, I'm done. What mathematical knowledge do we need for starting machine learning?
Probabilities. I think it's the most important part. Probabilities, a bit of calculus in order to understand the gradient descent, but now it's almost possible to do deep learning without understanding the true underlying things, but because the framework are very good. But yeah, calculus and probabilities, I would say.
For the approximation theorems, you need also some kinds of functional analysis. Yeah.
Yeah.
Mm.
Okay, are we good? So thank you for coming, and see you next month.
Yeah.
I'm not sure, it will be either ggplot or the Git one that we canceled last time. We'll see, but it will be a more beginner oriented talk. Thank you, everyone. Bye-bye.
Goodbye.